Bismillahirrahmanirrahim. Welcome to the course titled Advanced Digital Design or Advanced Digital System Design. And my name is Shoaib, and I'll be teaching you this course. And I've been, doing this for many years, but then for last 4 or 5 years, as a matter of fact, I have not taught in case. So it's like after a gap of 4 or 5 years. About the course, it's a course in system design, digital system design. That primarily means that taking an algorithm which usually is written in C programming or in Java programming or in MATLAB or in any other software programming and doing it in hardware. So it's a system where you map an algorithm in hardware on FPGAs, on ASICs. So it's almost a core computer engineering course. Where you learn how you primarily the tricks to map applications and algorithms in hardware, and there are several reasons why you do this. And at least in this lecture, we will understand why there is a need to do this. That instead of implementing algorithms in software, you implement them in hardware. So it's definitely an advanced course. So it requires some prerequisite knowledge for you to understand the concepts, and I expect people to know basic logic design, gates, flip-flops, a little about computer organization architecture, microprocessor architecture, ALU, and some very basic elementary definitions must be known to you. And as the algorithm of interest are primarily from signal processing, so a prerequisite knowledge of signal and system will help you to comprehend and understand or appreciate what we do in this course. So the prerequisite is also signal and system, digital signal processing. Luckily, the textbook is written by me, so this is the book which is titled Digital Design of Signal Processing System, and we have a pirated version of this as well. Ali is my TA in this course, and this you can actually get it for, this is an expensive book because published by John Wiley, but you can find a local copy, is perhaps 320 rupees, and we'll see how we can get you this book. So it's the same book, but published or printed here in Pakistan. And then the website, mostly you can get my lectures from this website, which says drshoaibkhan.com, and then there are 2 reference books as well, and that those of you who are not expert in Verilog, they may want to just go over this book, though we'll spend some time learning about Verilog. So it's Verilog by Samir Panitkar, and then there is another book which is Advanced Digital Design with Verilog HDL by Michael Slatey. So this is what digital design means. Digital design means taking algorithms and applications and mapping them in silicon, right? So in a single line, if somebody asks me to define the subject, so this is the subject. For example, I'll come back to this slide. This is very familiar code written in C programming language, and there is a way you write C code. You define your variables, you write functions, and in functions you have loops, and in loops you have actually instructions doing additions, multiplications, So in many applications you cannot just rely on, for many reasons, and primarily for performance reasons, you cannot just implement your algorithms in C language on a programmable processor. And there are many, so I'll be giving you examples. So the course is about, definitely as a first step, you do implement your algorithm in a programming language, and then you map them in silicon. And to do that, you need to learn several techniques. So this course is about the techniques. You apply transformations, there are tricks to do an optimal mapping. And once we say optimal, it means in many applications you are concerned about area, that you want your application to take minimum area, and in others you are more concerned about power dissipation, And then performance is very important, because you have to meet the performance that it's usually it is the performance which drives most of your design, that how fast you intend to process. And the testability also very critical issue. Usually designers ignore this very important aspect of digital design, that once you are designing, you need to put your thoughts for testing the design, because testing hardware is very difficult. Testing a piece of software is very simple because it's sequential. You can put breakpoints, you can put traces, you can do logs, and you can just, because it only execute one instruction at a time. Hardware, everything is alive all the time. If there are million gates, they all are alive all the time. And because they all are alive, so it's very difficult to find out where the bug is. You can only guess. You cannot just go and just trace it like you trace software. So that's why people spend a lot of time, energies while they are designing actually to put things, there may be additional resources to test your design. So testability you include in your design, not that you first design and then you test. So testability is a very important aspect of digital system design because of the complexity and the challenges it poses. So we'll cover all these, and then we know the advancement is very rapid, and because of the advancement, always it is adding new dimensions in the technology. There's always a lot more to learn. Where you stand today, tomorrow you'll find new things popping up in the market or in this particular technology. So it is honestly, the revolution you see in energy is because of the VLSI technology. Your handheld phones, you see the functions and features, it is just continuously they are adding a new product in the market. It's primarily because of the VLSI technology, advancement in the VLSI technology. So this is what again an algorithm implemented in C or MATLAB or Java will be converted into an architecture. For example, if I spend a little time, this is an algorithm which is primarily implementing an FIR filter, and you are taking if I write this as a summation or an equation, is so it's something like this. So this is the famous convolution summation. So the C code actually implements this. What C code is doing is that h of k is an array of constants, so you define this array of constants. So as you see here, this is an array of constant, which is 5, 9, minus 22, 11, 8. So these are numbers, okay? And this is the data, though I have just to give you an example. The data is an array of constant, but usually this is an array of variable where you're continuously getting data, maybe your speech or video. So data is streamed into your design. So data is something which is continuously coming into your design. And this primarily is, so to say, a dot product. For example, if I say L is equal to 10, so the summation runs from 0 to 9. So if you open this up, it says h0 xn plus h1 xn minus 1, and you keep going, and it says h. So h9 is the last time you multiply, and xn minus 9. So from signal processing perspective, what we say, xn is the current sample. So in your stream of data, the most recent sample you receive, and only tells you that you require the current and the 9 old samples actually to implement this algorithm. So this is, if you are doing it as software, it's quite challenging as a matter of fact in software, because every time you get a new data, you have to shuffle your array or use circular buffers. But all this algorithm is doing is taking an array of constant. There are 10 constants, and you are calling this h buffer, and to implement one instance of the summation, one output value, you have this array y. X. So X also has 10 values, but this is a dynamic array which is changing all the time. Every time you add new sample, it gets into this memory location or in this location of your X buffer, and the old value gets out of this buffer. So we also call this tap delay line. So continuously you get a data, you need to maintain this array X. H is a constant, and then in software you take h0, x0, multiply them together, add in a temporary variable. Then you take h1 and x1 and multiply them together, add in the previous sum to get a summation. Okay, so this is what it is done here, that sum is 0 and you are running this summation for all the values of h and then multiplying these together and adding into a temporary sum, and once you are done with 10 of these values, so you put this in your y buffer and you go, because as you can see I have taken more values of x just to show that first your x of n is this, then x of n is this. So it's a dynamic buffer which is changing all the time, so it's changing, but usually you don't keep so many values, you just keep a number of values which the number which is actually required, which is 10. So 10 samples are more than enough to keep in this buffer, but you have to update this buffer every time you compute an output value. So if you are doing this in software, yes, you can sit down and put two loops together. It's a block floating point mean, block filter mean that you are, this routine is not only computing one output sample, rather it is computing 5 or 10 output sample. It computes, runs this equation once, then again, and then again. So it runs it in a number of times. So, but there is an inherent limitation in software. And the limitation, if you look at this routine, obviously once you call this function, there is a cost of calling a function, because you have to save so many values on the stack and then you get into the function. And then once you are executing this function, we say there is this for loop. So you got to maintain this for loop. Okay, the for loop means there is always an overhead in software for running this for loop. For loop, what the for loop is doing, it's initializing. Then every time you run this one statement, just one statement, which is actually multiplying and adding into the sum, you need to come back and again check. So as it's here, you need to add k, it takes few cycles, k plus plus, then you need to do m minus minus, again it will take few cycles. Then you need to compare whether k is less than length of h or not. If not, then you go down and implement. If yes, then you need to branch. So just to execute one instruction, this, you spend 30-40 good cycles just to maintain the loop. So this is the overhead which you pay in software. Sometimes in signal processing application, your desires or demands or requirements are such you don't have these many extra cycles to waste. I mean, you just cannot call a function, you don't want your processor to wait in maintaining the loop just to execute one instruction, you know. So this all you are paying to execute one instruction. It's this huge overhead. It's like perhaps 90% overhead and only you're doing 10% work actually in this piece of software. And it is usually the case in signal processing. There's a for loop and another loop, another loop, another loop, because in software the actual processor can only do one multiplication and addition, number one. Number two, your mind thinks in that way. Your mind will not never think in terms of parallelism, because this is what you have learned. It's a sequential way of doing things, So this is the best you can do in software, and this is the main limitation, that though Pentium will be very fast, very smart, but it'll just stuck into doing all this, and that'll make it almost all programmable processor will have this inherent limitation. So once we say no, my requirements are such that I want to do this in a single cycle or 2 cycles or 5 cycles, depending upon how much budget I have, I need to come up with architectures, So once we say architecture, the code will change into a figure like this, right? So once you are drawing architecture, you say architecture. Architecture means, okay, you have this X buffer which you had in software as well, you have this buffer which you also had in software as well. So these are the buffers, and obviously you need to access, like you do pointers and you get X, you get H, you multiply. But you say no, I don't. First of all, you are not wasting any time in maintaining loops, calling functions. It's just data comes into this buffer directly and it just gets updated. The whole thing gets updated. So new value comes in, old value goes out. So you are not really doing any piece of software. Actually, it's just the hardware which is taking a value and throwing the old value away from the register at the bottom. So it's automatically working in lockstep, and then H you just put it in a ROM, means it's all the constants, and then it's up to you that how many multiply. This is the beauty of hardware, whether you want to multiply, do 1 multiplication addition, 2 multiplication addition, 3 multiplication addition, 4 multiplication, it's all in your hand. and definitely it depends upon the resources you have on your device, but it's in your hand. You find out, you sit down, you do your calculations, know that at what rate you are getting the data, at what rate you have to produce the output, and then you say, okay, I think 4 multipliers, they are good enough to give me the required performance. So this is the difference between doing things in software and implementing things in hardware, and that the same algorithm, the same understanding, comprehension, knowing your requirement, and then drawing these circuits or drawings at a level of abstraction. The good thing about hardware design is that you really need not to know the VLSI to actually implement this. You need not to know about the transistors and the circuits and the layouts, and the current tool provides you a level of abstraction that, knowing programming, you can design hardware. That's the beauty of the course, that you have a level of abstraction where all you have to do is your mind must able to at least draw this. This is a requisite. So you say, I have drawn this, then it is just a language like C, which most of you must be knowing. It's Verilog. Then you just sit down and write your code. And it's much easier to write Verilog than to write C. So that's another comfort which we get, that there are no pointers, there are no pointer to functions. There's so many things which are not there in Verilog. So Verilog is a dumb, simple language. The reason it is dumb and simple, because it got to be, by a tool, it got to be translated into hardware. So they have to keep it very dumb. So it's a very dumb language. It's very simple to learn language, especially the part of the language which translates into hardware is very simple. So this is what the course is about, that finding out ways of taking different types of algorithms into hardware, then actually implementing them, seeing that they get into hardware, seeing their layouts, and actually running your simulation, and see if we can give you a hands-on onto actual doing this on FPGAs. So the other type of algorithm, because our main interest, though, we spend time learning about the algorithms in networks, and that's what we are, the type of work we are doing. So doing a lot of stuff in networks, because networks, the challenges are different. In networks, obviously, now you see 10 gigabit, even 100 gigabit interfaces, 100 gigabit of serial interface. So getting data at 100 gigabit, obviously no piece of software, no software machine can handle that type of throughput. So people have no other option but to do these things in hardware. So networking applications. So networking applications are there where you are working on the interfaces, you are doing your routing, your forwarding, your stuff like that. Then there are multimedia, image processing, pattern recognition, neural network, and you just name applications. There's a host of applications. Sometimes we like drawing an application like a flow graph, especially in signal processing, FFT, DCT, So there are several algorithms which are best explained by drawing it as a flow graph. And flow graph is not an architecture. Flow graph is just a way for you to comprehend an algorithm in a better way. And so FFT, as most of you, those of you who have taken, must be a signal processing course, a basic signal processing course, must have seen this full of butterfly structure where your data is 8-point FFT. These are your input values. So this value gets added into this value. It goes here. So it's a way of expression. So sometimes you say not the algorithm or an implementation in C will better help you to implement that algorithm in hardware. Rather, it is the flow graph, because flow graph gives you better visualization of the activities in that algorithm. So sometimes you say, let's draw a flow graph. So flow graph will give you an easy mapping. But flow graph, again, is not an architecture. Flow graph is an expression of an algorithm. So this is a flow graph of fast Fourier transform. And this is a hardware implementation. It's very interesting, not very easy to conceive design, where if you count, these are 1, 2, 3, 4 butterflies. Okay? And in every stage you have 4 butterflies. So it's an algorithm which requires you to implement in software, if you're doing it in software, 12 butterflies. Okay? And now a hardware mapping, what it does is that instead of implementing 4 butterflies, it actually, in hardware, it only design one butterfly. So once at every stage there is one butterfly. What you see is the hardware. One butterfly, and one butterfly. So these are and these are the things, just a lecture in introduction where I'm just giving you a taste of the subject, that what you will be seeing in this course. Not I don't I'm not assuming that you learn whatever I'm saying you right now, but it's just to show you it's a trailer basically what you see in a movie. So this is another scene in the movie where you see all these butterflies. 4 of these get mapped onto one. So 4 butterflies get mapped onto one. And now the beauty of the architecture is that it works in lockstep. It automatically maintains the data to be forwarded to a multiplier and adder in a fashion that once this butterfly gets implemented, then the requisite data at the input of the butterfly is already there. So what you see here, the muxes and the registers, they are placed in such a fashion that intermediate values are stored. For example, this butterfly gets implemented first, but this butterfly cannot be implemented because this input requires this butterfly to be implemented. Has not yet been implemented, so it maps one, then it maps another, then it maps another, and the intermediate structure of registers and multiplexers ensures that the right data to the right butterfly at right time, so that it works in lockstep. So the data is coming in and it's going out, and these are another type of architectures which we design. And then yet there are more challenges. The challenges are actually taking something very complex like MPEG. Let's say you want to design an MPEG chip. So if you are designing a chip or an MPEG encoder or a decoder, I think the most important aspect of that design is doing the top level, that how you perceive the whole thing, because usually a bigger system like MPEG, like JPEG, like a communication transmitter receiver, like a router, like any application you take, and once we say the whole thing, let's design the whole thing. The whole thing requires you to think in terms of the top level design, that how are your data is going to flow across your design. Where are you going to store your data? What is the top level design methodology? It's very critical and important, and to learn the top level design way of doing the whole thing, and then worrying about the components, the discrete cosine transform, the quantizer, the decoder, the inverse quantizer. You know, these are the blocks. You say first I'll put the whole as it's just like a problem in architecture. You know, an architect would sit and first of all he'll just put bedroom and drawing room and bathroom and stairs, you know, just at the top level. Then you go get into the details, you know, that the flow is important, the ergonomics is important. The same is the case here. The data movement is important, how you are saving the data, how best you can design that the people can work independent of each other, the groups can work independent of each other, how best you can design that people can test their component in a way, once they put these components together, the whole thing will work. I mean, so these are the challenges in the top level design, and again we will spend time in learning that how you do the top level. The top level first of all will spend time that okay, you are given a problem and what are the best ways of putting the whole thing at the top level together, and then what are the design options to do the blocks. Okay? So here this brings me to the course outline. We'll spend some time, very quickly we'll go over the Verilog. So I expect people to know Verilog, but still we'll spend some time to learn about Verilog. It's simple to learn language. At the same time, I'll spend time in covering, just touching System Verilog and System C. System Verilog, though they are also great languages, but still the synthesis tools, most of the synthesis tools, they don't support these languages. Mostly these are used for stimulus and just testing your design, but they are there. People are spending time in developing, evolving even better languages than what Verilog offers you, and then we'll spend time in learning about floating point to fixed point conversion, and then we'll come and spend time in learning about the top level design. What are the design options we have to do a top level design without really worrying about what goes inside the blocks. And then we'll spend time learning about the FPGAs and field programmable gate arrays, their architectures, what they have to offer today, what they were yesterday and today. They come with several embedded blocks. They have multipliers, like you can easily define an FPGA 500 multipliers. So 500 multipliers at your disposal. So you need to know how to best utilize these type of resources. There are adders, there are carry chains, there are interfaces built into the FPGAs. There are embedded processors built into the FPGAs. So basically, now FPGA is not only hardware; it's also a software that runs in those FPGAs. So you can boot an FPGA with a PowerPC in it with a Linux, and so you have a programmable machine sitting right there on the FPGA, which you can use to control the other parts of the FPGA or your resources. So we'll spend time learning about all these things. And then there are tools, and the tools are like system generator, which can help you to do most of your work. If you are in a professional setting designing something, there are things which you can just design by automatically generating the Verilog code. So there are cores which you can design, the blocks which are already there. So we need to know all the resources we have, and then how best you utilize those things. What are the issues in logic synthesis once you are actually writing Verilog code and synthesizing it. So after spending time on these topics, we'll then move to actually designing the inner blocks. As I mentioned, we are going almost in the same fashion, learning about how you take algorithms usually written in floating point, convert them. This is a fixed point implementation, or representations. We'll spend time in representations of algorithms as well, and then doing the top level design. Do the top level, then we'll get into the blocks. And in the blocks, there are then techniques which we need to know, though they are the very basic building blocks like adders, multipliers, compression trees, shifters, multiplexers. So all these will spend time learning these basic. We'll spend more time in the advanced stuff like the parallel architectures. The fully parallel means that the way you draw, you actually implement it in the same way. So the easiest to design is this is the algorithm description in a flow graph. Just do the same hardware, do the same in hardware. Wherever there is an addition, you put an adder. Where there is a multiplication, and many people, they try to do this. If you ask somebody to design, usually this will be their first preference because it's very easy to design, but disastrous as far as the area or the resources are concerned, because mostly you don't need your algorithm to work in parallel. That you don't need to do everything in parallel because you don't have those type of requirements. So it's very rare that you need to do things like this. Mostly you need to come with creative way of doing things like this, where you are minimizing your resources and just getting to the required throughput, whatever is required by your application. So that brings us to learning about the unfolding, the pipelining, the retiming, the look-ahead transformation, the C-slow retiming, the parallel processing. And in many cases, it is quite opposite, that you even need to do more than what the algorithm tells you to do. So it's like especially in many of our applications, we are doing massively parallel systems. Massively parallel means that you got to do a lot more. You have to exploit parallelism at every level, at the lowest level, at the highest level, and how you design those systems. I'll be sharing some of our experiences in designing these parallel processing systems. So then I'll come to another interesting topic, which is the time shared architecture, where actually you are folding, and the folding means that like this is a good design where you have folded the design by 4. So by 4 means you are only using 1/4 of these resources. You can fold it by 12 times as well. By 12 times means there will be only one butterfly. So one butterfly, you use it 12 times to do your FFT. You can fold it by 6, by 2, by 3, by 4. So that's where the challenges are in the design, that knowing that how much amount of folding you need to do of an algorithm, that is quite challenging. Sometimes you can come up with an architecture where data will flow smoothly, but in most of the cases you need to maintain your data. You need to bring the data to the right part of your architecture at right time. So, but the folding, we'll spend more time learning about the folding, and then that'll take us to designing state machines in hardware, and then microcoded state machines. And microcoded means almost a programmable processor, almost. So we'll learn that sometimes the best way to design architecture is not by just holding, looking at the algorithms, because in many cases algorithms are so complex. Okay, for example, image processing is simple, video processing is simple, error correction coding is simple, speech compression is very complex.